So I hope you're able to see my screen.
Yes, sir.
Yeah, thank you. So we'll click on new steady state simulation, and it will ask us to enter the components. So we were doing methanol water system. So just selected methanol, selected the methanol. Now we'll enter the water into the water system. Now I have to select the thermodynamic property package. So we have selected NIST modified UNIFAC thermodynamic property package. We can also select NRTL. Both are acceptable because this is a liquid mixture. So just click add, then go to next. The system of units we need to select and finish the button. So I have to get the material stream first. So I will drag the material stream and I can zoom in to make it big. So once I click on the material stream, this window will pop up. So this is the feed stream. Once you enter the name, press enter, then that will reflect. Can anyone tell me what this flash spec means? Flash spec means temperature, pressure. What does it mean? Flash specifications. What this flash spec refers to? Any guess? What is the reason for flash specifications?
So I guess the user has to specify these values.
These are to specify.
Like for example, here temperature and pressure should be specified by us.
Why we need to specify?
So to get the properties from at that temperature and pressure, I guess.
Yeah. So according to this degrees of freedom rule, for a single pure component, we need to specify minimum of 2 properties. So temperature, pressure, flash specification refers to we need to specify temperature and pressure. I explained in the last class, right? So degrees of freedom calculations for a single pure component comes to be 2. C minus P plus 2. So we need to specify a minimum of 2 properties. Then only we can estimate rest of the properties using the thermodynamic property package. So since we need to specify any of the 2 properties, there are temperature, pressure, pressure enthalpy, pressure entropy, pressure vapor fraction. These are the flash specifications. So without specifying these 2, there is no way of calculating the properties of a pure component using thermodynamic property packages. Since this whole software is running based on the thermodynamic property packages, this is the minimum requirement for estimation of properties of a pure component. So that's what the flash specifications refers to. I hope you understood now. I'll just close my room door. Just give me a minute. Okay. So we want to see the flash separation. So here separators and tanks. This gas liquid separator or compound separator both refers to the separation of vapor and liquid or gas and liquids. These are the simple flash separation columns. These are the simple flash separation column. This tank is by the gravity settling. If you want to do separate two liquids by the gravity settling, then we can use this tank. So we use this gas liquid separator. So what is the minimum requirements for this flash separation? Anyone remember? What are the minimum requirements? This is showing red. That means we haven't given the minimum requirements. We haven't fit the minimum requirements. What are the minimum requirements for a flash separator? Or minimum
one inlet and two outlet streams.
And energy stream.
And energy streams.
Yeah, correct. So inlet feed and one vapor stream. I can click here to collect the vapor stream, and I can click here to collect the liquid stream. So as soon as I give a minimum requirements, it will turn to blue. Now we know to create the energy stream. So once we given the energy stream, right, we need to set overriding separation temperature. We need to specify the separation temperature or separation pressure. Either of two needs to be specified. Either of two, it doesn't actually take, in the earlier versions of DWSIM, if I enter the feed temperature, that assumes to be the separation temperature, but in the latest version, it does not take the feed temperature as the separation temperature. That's where the it gone wrong in the last class. So the temperature has to be between the bubble point temperatures and dew point temperature, right? So we can find out what is the bubble point temperature, what is the dew point temperature, and what is the vapor liquid equilibrium data for the system. Can anyone tell me how do we find out in this software, DWSIM software, bubble point temperature, dew point temperature, and the vapor composition and liquid composition at any intermediate temperatures? Some other than Varun? Using this software, how to find out bubble point, dew point temperatures, and the vapor liquid compositions at the temperature between bubble point and dew point temperature. So we can. Anyone, students respond, or do I need to call the names? People leaves as a scroll. That's a good thing. हाँ क्लास के बाद आए. Okay, Aryan, Jyotiraditya Aryan, do you remember? So 11, 17 or 15. Aryan, Jyotiraditya Aryan. Are you there? Nidhi Raj, are you there? Yeah, Jyotiradityan, since if you are there, how do we find out bubble point temperature, dew point temperature of this methanol water mixture using this software? Do you know or not aware? Okay, that's good. Ayush Surana? Are you there, Ayush? Okay, Lalit. See, I need students' involvement. Otherwise, no use. Yeah, Ayush, tell me the answer. How do we get the bubble point temperature, dew point temperature of this methanol water using this software we discussed in the last class? Okay, Bhavana Kumari, do you remember?
Sir, actually, I am unable to recall it from the last class.
Okay. So probably didn't get time to practice.
Sir, actually, my laptop was not working fine, so I didn't practice it.
It's okay, it's okay. Nidhi Raj, are you there or not?
Yes, sir.
Yeah. Do you remember anyway?
No, sir, not.
Okay. See, if you don't remember, you can unmute and say don't remember. Otherwise, if you don't answer, I assume that you just logged in and you gone somewhere. So as I said, I'm marking everything. Of course, if somebody don't remember, I don't mind. But if you say yes, present, then that will be better. Because I wanted to teach to students, not to the computer screens. So basically, we use utilities option. We see here, I just clicked utilities option here in the top. Here, if I click add utility, then this window will open, add utility. So we can select utility option to material stream. We can select to separation vessel. Then we can also do the utility operation to valves. For different thing, you will have a different utility options. So here we need to select the material streams because in this material stream, methanol and water is present and we wanted to find out the vapor liquid equilibrium data. We need to find out the vapor liquid equilibrium data. So binary phase envelope gives the vapor liquid equilibrium data. Ternary phase envelopes gives the liquid equilibrium data. Like when you have three components involved, ternary phase. Binary phase, when you have two components, we use the binary phase envelope. So binary phase envelope, and I select the feed stream. I select the feed stream because I know in the feed stream both methanol and water is there. I know in the feed stream, methanol and water are there. So I select material streams, binary phase envelope, and feed stream, click add utility. So as soon as you click add utility, your flow sheet will not be disturbed because in the flow sheet tab, flow sheet will be remain as it is, and there will be new tab will be open, which is called binary envelope. So whenever we have the mixers, methanol water mixers, since we wanted to find out the mixer properties, not the pure component properties, we wanted to find out the mixer properties. So when you have a mixer, if you do degrees of freedom analysis, you will get the degrees of freedom to be 1. Degrees of freedom to be 1. So you need to specify one property. So T or P we need to specify. So we can draw TXY diagram or PXY diagram. We can draw TXY diagram or PXY diagram. So methanol water, whatever highly volatile component should be selected as compound 1, and low volatile component should be selected as a component 2. And here we have TXY data and PXY data. So here we can select VLE data, LLE data, or SLE data. So, and mole fraction is the basis, x-axis, 0 to 1. So whatever compound 1 we give, those mole fractions will be displayed here. And fractions ranging from 0 to 1, because we wanted the vapor liquid equilibrium data from 0 to 1, we will have to select 0 to 1 and calculate. If I calculate, I get this. If I calculate, I will get this. So this is the methanol water systems vapor liquid equilibrium data. Last class I showed you ethanol water. In ethanol water above mole fraction of 9, you will see x equal to y line. X equal to y line. But here in methanol water, you don't have such thing. Even if you use the non-ideal thermodynamic property package. Non-ideal thermodynamic property package. So this is the, now in this one, which is the bubble point curve and which is the dew point curve. Here we have two lines, which is the bubble point curve and which is the dew point curve.
Lower one bubble point, upper one dew point.
Yeah. Lower one is bubble point. You can see here also clearly mentioned. And here upper one is dew point line. Dew point line corresponds to the vapor mole fraction, and bubble point line corresponds to the liquid mole fraction. Corresponds to the liquid mole fraction. So the bubble point is, here you can see 337 degrees centigrade. The bubble point is 337.75 degrees centigrade is the bubble point, and dew point is, you can see 373. From this VLE curve, we can get bubble point, dew point, and the vapor liquid compositions between bubble point and dew point. So this is the dew point, 375. So this is the dew point line. This is the dew point. And this is the bubble point temperature. So now I hope you all understood. So how to get this vapor liquid equilibrium data and bubble point and temperature, because this is important for the distillation calculation. This is the temperature important for the distillation calculations. So we'll go to flow sheet. Let's say I wanted to set the desired temperature as 350 Kelvin. So I wanted to set the desired temperature as 350 Kelvin. Now we can see, if I set the desired temperature 350 Kelvin, the vapor composition will be around 0.7. The vapor composition will be around 0.7, and the liquid composition will be around 0.35, around 0.35, because I just clicked. No.
So right click and click on unzoom.
Yeah, thank you. Yeah, thank you. So at 350 Kelvin, so we know that it will form liquid vapor, vapor liquid, and from this envelope we can calculate the liquid temperature and we can calculate the vapor temperature. So go to solve flow sheet. Flow sheet. Now we will set the desired temperature as 350 Kelvin. 350 Kelvin. Then we run the flow sheet. So here you can see this is the vapor composition. In the compounds we can see methanol 0.7, water 0.299, that is 0.3. Similarly, in the bottom liquid, you can see methanol 0.34 and water is 0.65. Exactly, you can see that. Here 350, you'll get vapor of 0.7, 0.7 and liquid of 0.35. Liquid of 0.35. So exactly in a simple flash separator, what happens is if you introduce a feed liquid at a temperatures between bubble point and dew point temperature, so assuming both liquid and vapor in equilibrium, as soon as you introduce that liquid mixture into flash separator, we get a vapor comes out and we get a liquid comes out, and the liquid composition, vapor composition is depends upon at what temperature you are maintaining. Now this energy stream tells us that, so we have feed at 298 Kelvin and basically you are separating temperature 350 Kelvin, and this much amount of heat you need to produce using a heat exchanger before we introduce into flash separator. That's what this energy stream tells us. So we have feed temperature at 298 Kelvin and we are doing the flash separation at 350 Kelvin. So prior to this flash separation, we need to heat the feed liquid. You need to provide this much amount of energy. That's what this energy stream is tells about. So, so if you know the desired set temperature or desired set pressure, we can easily know the flash separation. We can easily get the flash separation. So now that we have seen the vapor liquid equilibrium data, I'll just also show you how to get the LLE data. So I'll just close this and open new one. And I wanted to show you how to generate a liquid equilibrium data. So I'm just selecting three components for the liquid equilibrium data: water, and I'm selecting ethanol, and hexane. So here I have selected three components: water, ethanol, and hexane. Okay, water, ethanol, and hexane. So which property package I should select? Any guess from the students? Which property package should I select?
So I guess NIST again.
NIST again. Okay. Any other thing also we can select?
I guess cow cedar because we are dealing with hydrocarbons.
Okay, but is there? I don't think there are electrolytes, no, cover cider for the electrolytes, right?
Oh, yes, sir.
So we can select NRTL and we can also select NIST. By default, as soon as a liquids, by default we can select NRTL or we can select NIST. So go with NIST. Add. Suppose I will just show you. Okay, if I select something else, sometimes some of the databases may not have the interaction parameters, so then you need to select the other thing. So we just drag on material stream, temperature, flash specifications, and for anyway for the liquid equilibrium data or vapor liquid equilibrium data, doesn't matter what specifications we keep here. Utilities, add utility, material stream. I need to select the ternary phase envelope because we wanted to get the three components. We have selected the three components, and this material stream one which contains three components, which is water, ethanol, and N-hexane. All the three components are present in this material stream. So I should select ternary phase envelope, then flowsheet object 1 and add utility. Since I've selected the ternary envelope and we get this sort of diagram. I'm sure you have seen in the mass transfer. Guys, have you seen this type of LLE diagram?
Yes, sir.
Yeah. So water, ethanol, and hexane, I have selected these three components, and at room temperature, atmospheric pressure conditions, we are doing this and calculate diagram. So once you calculate diagram and see, this is the liquid equilibrium data, what it shows. Now, see these lines is the water rich, and these areas are the ethanol rich, and these areas the hexane rich phase. So if we, based on this curve, we can select what concentration of the solvent we need to use to separate the solute. We can use the water ratios of the solvent conditions we need to use to separate the solute. And using this diagram, we will also estimate the number of theoretical trays required for the liquid extractor. Whatever exactly we've done in the distillation, we can do same in the LLE diagram using this diagram. Definitely would have learned in mass transfer how to estimate the number of theoretical stays and tie lines. So these are the tie lines which corresponds to the Y versus X data. We can also plot this even simple Y versus X data also for the convenience sake. So just I showed VLE, vapor liquid equilibrium data. Just similarly, we can also generate TLE, ternary envelope, that is LLE, liquid equilibrium data. So this data is really helpful. Without this equilibrium data, you will not be able to do any of this extracted design or absorber design or distillation column design. This equilibrium data is very, very important. So that's about the flash separator. Now, so I have showed VLE, LLE, and flash separation. Now we will move on to the distillation. We want to move on to the distillation. So in the distillation column, we wanted to separate miscible liquid mixture, having significant boiling point you can separate distillation. Distillation primarily used for the miscible liquid mixtures having the significant boiling difference between the components. So typical design of a distillation column involves how many number of trays required, in a distillation column. I'm sure you all know distillation column, right? We have many intermediate trays. Probably I don't need to draw a distillation column diagram because you might have seen very much in a mass transfer. So the number of trays required, first of all, we calculate number of theoretical trays required. So we can use graphical procedure for this. And we also have the simple method, Pensky equation. Pensky equation primarily used for the total reflex conditions. And we have for the for non-total reflex conditions, we have the any method. Do you remember what are the methods we can use? Any student remembers any methods we use to estimate the theoretical trace? McCabe-Thiele method. That is graphical procedure, no? Graphical procedure is McCabe-Thiele method. That is the graphical method. And I'm asking about non-graphical. Pensky equation. Any other equation is there? Do you remember? Gilliland method. Have you heard about? Gilliland method. So this is in Underwood-Gilliland method. What we do is we will write the mass balance for each tray, and we solve all these equations. We solve all these mass balance equations to find out the expression. Same thing what we do in the McCabe-Thiele method. McCabe-Thiele shown in form of graphical representation, whereas these guys shown in terms of the mass balance expression. Both are same. I'll show you how it's both are same. So since we wanted a equation, because when you write computer program, we always prefer to have the equations, and this Gilliland method is commonly used. This Gilliland method is commonly used for the distillation column to find out the number of theoretical trays required for the distillation column if you use any process simulator software. Process simulator software uses this method to find out the number of theoretical trays. So once you find out number of theoretical trays, number of actual trays, how do you find out number of actual trays from the theoretical trays? So number of theoretical trays divided by what will be here to find out the number of actual trays?
Efficiency.
Yeah, tray efficiency. So I think you guys knows this in your design PD2. So number of actual trays. Now another important parameter which controls number of theoretical trays. Important parameter which controls theoretical trays, number of theoretical trays. Theoretical trays is reflux ratio. So what is the usual guidelines for the reflux ratio? Anyone can answer me? Maybe Aryan or Aishwarana, can you answer? Reflux ratio we should be, what will be the reflux ratio we usually maintain in the distillation columns? Any other student? What is the usual reflex ratio we maintain in the distillation columns?
Around 5%.
Sorry,
Around 5%.
5% of what?
Of the minimum reflex ratio.
So, is Raman is answering?
Yes, sir.
Yeah. We actually not 5%. We will use 1.5 times minimum reflex ratio. Higher. Understood, Shraman? So we won't use 5% of minimum reflex ratio. We will actually add 1.50% additional of the minimum reflex ratio. So 1.3 to 1.5 times minimum reflex ratio we will use in the distillation column. So how do we find out minimum reflex ratio? Anyone remember? How do we find out minimum reflex ratio? So let's say this is like this. This is y, x, and so this is the yd. Sorry. So this is the required distillate composition. So this is the yd. Now, how do we find out the minimum reflex ratio? Anyone remember?
We can draw the feed line, join the distillate on the operating line to the point where the feed line intersects the equilibrium curve. And then from the slope, we can find the...
Okay, so this is the feed line. Now this is the XF. Now from here, how do I draw the feed line? Should I draw straight up, or should I make some inclination, or should I do which one? Let's say 1, 2, 3. So which way I have to connect from here? So 1, 2, 3 is depends on what?
Whether the feed is pure liquid or a mixture of liquid vapor.
Yeah, correct. So it depends upon the feed condition. If it is purely vapor, a mixture of liquid vapor, this is called Q line, right? You might have remember Q line slope. Q line slope. So yeah, you're right, Shravan. So once you know this feed line, and we can join these two lines. If it is falling to line 2, we can join two lines, and from this we get xd by rm plus 1 or yd by rm plus 1. xd by rm plus 1. So rm plus 1. So this is the minimum reflex ratio. Reflex ratio is very, very important. It plays crucial role. And then we multiply with this Rm with 1.5. Then we draw this line. Then we do the number of theoretical trace. So we can do all this calculation using this software in a quick way. In a quick way. Yeah. So yeah, I wanted to give an industrial problem. So styrene, in the styrene production plant, in the styrene production process, after the reaction, styrene and ethyl benzene will be there. Styrene, ethyl benzene will be there. So ethyl benzene needs to be separated from the styrene because we need to recycle back the ethyl benzene. So typical stream leaving the styrene reactor will contain 0.455 mole fraction of styrene, 0.585 mole fraction of ethyl benzene, and then the trace impurities of heptadecane will be there. Heptadecane will be there. So this will be 1 minus. So this is the, put more, 58. Very small quantity. Yeah. So this is the, in the styrene production, the stream leaving the reactor contain styrene of this mole fraction, ethyl benzene of this mole fraction, and heptadecane of this mole fraction will be there. Usually the stream leaving the reactor will be at 110 degree Fahrenheit. 110 degree Fahrenheit. So we wanted to design a distillation column, or we wanted to estimate for designing distillation column, we wanted to estimate what is the minimum reflux ratio and what is the theoretical trace required. All these things we can easily calculate using this software. So I just click new one. So I'll select three components. Since we need to deal with three components: styrene, ethyl benzene, and here we have heptadecane. So we have these three components. So since it's the liquid mixture, for convenience sake, easily first thing goes to is NIST and NRTL. So I'm adding NIST and going to the next. And since I'm having the degree Fahrenheit and all other thing, I can go for English units. So this gives the most of the English units, that is FPS units. So degrees Fahrenheit, pressure, and all these conditions we can easily maintain. So for a distillation column, always the feed will be liquid mixture. So I need to get a material stream first. So I need to define, this is the feed stream which is going to the distillation column. Feed distillation column, and here it is taking by default a 77 degrees centigrade. But as I said, the temperature is 110 degree Fahrenheit. The stream leaving the reactor will be at 110 degree Fahrenheit. And it has taken some mass flow as 7936 lb mass per hour. So I've just kept it the by default value. Now we need to enter the mole fractions. We need to click on the compound amounts, mole fractions. So given mole fractions is styrene 0.422. 0.422. Then ethyl benzene is 0.575. 0.575. And heptadecane is 0.003. 003. Once you enter all the three mole fractions, always check that total is 1. Because sometimes we may enter wrong number in the while you enter in the quick manner. So you'll always cross check the total mole fraction is 1. And after that, don't forget to press accept. Unless you click accept, these mole fractions will not be reflected here. The mole fractions will not be reflected here. Class. So here I have given the feed stream. Now I wanted to see the distillation column. So we have seen the separation, then we have seen the mixing stream. So exchanges, we don't want to talk about heat exchangers, reactors. Right now we'll go to the columns. We'll go to the columns. So here we have 4 for the normal one, and this is for the pro software. So so we can use shortcut distillation column and distillation column and absorption column. The ChemSep column is the additional interface. It is not the directly from here. So whatever you're doing, all the three, you can also do in the ChemSep column. So distillation column and shortcut distillation column, there are two, right? In the shortcut distillation column, you can get theoretical trace and small, only those calculations. But if you want to use for intermediate stream separation, like crude distillation unit, then we have to take this distillation column, which gives the more details. So for today, we will see the shortcut column. So just drag on the shortcut column. So distillation column needs these 5 streams to be specified. All these details need to be specified. So the feed stream will be the feed, and distillate stream, since I don't have any streams, I'll just click on here to create it. Then bottom stream, I'll just click on this. Then condenser, I need to click on a condenser. So this is the condenser heat duty. Then reboiler heat duty. So this much amount of energy needs to be given to the reboiler. Now what is the light key? What is the heavy key? Software doesn't take by default, because here we have only 3 components. And so based on relative volatility, we can decide which is light component, which is heavy component. So ethyl benzene is the light component and styrene is the heavy component. So light key is ethyl benzene, heavy key is styrene. And here you can see light key always comes in the distillate. Light key comes in the distillate. Majority of the light key comes in the distillate, and majority of the heavy comes in the bottom stream. So LK, light key mole fraction in the bottoms. You can specify because here when you design a distillation column, we design to get this much separation. We design to get a required amount of separation. We design a distillation column to get a required separation. So we wanted to say the ethyl benzene, which is high volatile component, should be there only 5% in the bottoms. That means in the bottom, 95% should be styrene or styrene and hexadecane. So 5%. Heavy key mole fraction in the distillate, like styrene in the top, how much it has to be. So let's say I'll just give 3%. And here reflex ratio is 1.5. Reflex ratio is 1.5. But here because we don't know. Ideally, we should select 1.5 times the minimum reflex ratio, but initially we don't know what is the minimum reflex ratio. We don't know what is the minimum reflex ratio. So we just take some random value. We just take some random value and we calculate it. Let's say we calculate it. We calculate it. What's the error?
Sir, I think it's the 0.05 and 0.03.
Oh yeah, correct. Mole fraction. Thank you. Yeah, thank you, Varun. So LK mole fraction in 0.05 and 0.03, and initially we give reflex ratio is 1.5 times because we don't know what is the minimum reflex ratio. So it calculates what is the minimum reflex ratio and what is the minimum number of theoretical stages. And since we have given, since the reflex ratio given here is lower than minimum reflex ratio, it doesn't display actual number of stages and optimal field stages. So we have to give 4.3, 4.3, that is the minimum reflex ratio. Is 4.3. So 4.3 times 1.5, so 6.45. So now if I give 6.45 and it calculates. Now I have given 1.5 times the minimum reflex ratio, so that is 6.45. Now it is showing actual number of stages and optimal field stage. So just the advantage with this process simulators is that just by doing the simple feed and product conditions, whatever we have done in our course, in mass transfer course, like McCabe method or Gilliland method, those are programmed to give a quick results, So that's how we find out this minimum number of theoretical stages, actual stages, reflex ratio from using this shortcut column in the DWSIM operation. And DWSIM. So next class we will see absorption and the distillation column. If time permits, we'll move on to the reactors. Any questions, students, from your side? It's already 12, so I'll stop it here. So I will upload these files and please do practice. Please do practice it, and so that you will be able to follow better. Okay, students, thank you. If no questions, you may leave.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.